Okay, so last time, I think this is where we stopped. Basically, we discussed about the difference basically between the CFD simulations that we have encounter or will encounter, and compared to that, the one that we are looking at on this page. For example, this is the von Karman vortex, and this is simulation, of course, and this is from experimental study. So you can see that from the CFD results over here, the behavior of the von Karman vortex is simulated or replicated nicely. The question I had last time was why the one that I showed before as some examples did not show the behavior that we are looking at right now, the wake, okay, the von Karman characteristic here. So the answer for that was because we are using grants method in solving our problems or our simulation. Okay, so basically what we're going to study later on in turbulence model, which I think after we finish FDM. So we're going to look at the difference between LES. Okay, so we are going to look at the difference between the LES model, large eddy simulation, versus runs. And of course, before LES, we have E and S, direct numerical simulation. Okay, so we're going to discuss this later on after we discuss the FDM, right? Okay, so all right, so let's proceed. Okay, so what we are going to cover in turbulence modeling later on. So if you look over here, so this is quite similar to what we have before. So this is the von Karman vortex, or the characteristic of von Karman phenomena. So simulation, and this is the experimental result. Okay, what or why we are looking or why we have something like this is due to the phenomena that is called as vortex missing. Okay, so later on we're going to have a look. This is just a preview. So we have an object. So this is our object. Okay, and we have a mean flow, meaning that this is at free stream velocity. Okay, u free stream. So when the flow pass through an object, so what you're going to have is the vortex. This is eddy. It can be vortex, it can be eddy. So basically, the eddy or vortex just meaning that the flow is curling or mixing together. Okay, and if you notice over here, the size of the eddies, eddies mean the curl arrow over here. So the size of the eddies, the vortexes, the mixing together, they are different. So first, it can be quite large, right? After the, it can be quite small or large depending on the problems. But the size can be different. It can be large eddies and it can be small eddies. Okay, all these are mixing together. Okay, so the size of the eddies can be further characterized by the name. Okay, so they call it, for example, energy cascade. Energy cascade means the energy is being cascaded from a large eddy to a smaller eddy. So this is what we're going to cover later on. So we are going to look at, in terms of turbulence, this is what basically some the highlights or the gist of it's not summary, but let's call it summary. Summary of what you're going to look in turbulence. Okay, turbulence means violence or hardcore mixing of flows due to eddies. Eddies means rotational characteristic of the flow. So all these turbulence, eddies, vortexes mixing together, and it can be further characterized by the size of it. So this is what we're going to study later. Okay. Okay. So we discussed before. Basically, if you have CFD output, okay, you have to validate your output with experimental value. So this is an example of a good validation. For example, let's look at the CD, drag value or coefficient of drag here. So the CFD value and also the experimental value, they are quite close to one another. So this basically indicate that our CFD output is reliable. Okay. So sometimes get confused. So if I, for example, if I write something like this, if you have experimental result, you have CFD output here. So the correct way that we should say, or we should understand, is that experimental value must be used to validate CFD. Okay, we cannot say CFD is used to validate experimental values. So there are two different things. Okay, because CFD basically is an estimation. Remember, we have to make several assumptions. We have to make several modifications or simplifications of our domain, for example. Okay, for example, again, if we use runs model, okay, runs is just an average value. Okay, it cannot capture the exact velocity profile at a specific location due to the approximation method that you use. Okay, so for example, if we use runs, then we cannot capture the real phenomena that is happening for the experimental value. So that is why when you use CFD, it needs to be validated either by using experimental or analytical. Okay. You cannot say CFD is used to validate analytical. It's the other way around. But you can say that CFD is being used to check or to compare. Okay, it cannot be used to verify, but it can be used to compare the results from experimental or analytical. Okay. All right. So we look at one examples regarding the domain of, for example, the stator axial flow fan before. So how we can create the domain. So this is what we looked at before. We have the inlet velocity on the left, and then we have the pressure outlet. Remember, we discussed about the domain, how to set up the domain, how big your domain should be. Okay. So in these examples, instead of drawing, or instead of looking at the design as a whole, so they just focus the domain between blade 1 and blade 2, just between two blades. Okay. So in CFD, for example, in lab 1, you look at how your calculations or your simulation can be simplified just by using symmetry boundary condition. Okay. So by using that, basically you, okay, for example, if you have pipe, okay, you simplify your diagram, your geometry or your mesh or your domain by using just half of the object's dimension, because it is symmetry, so that you can save on computational resources. So similarly, this is what is being done here. Instead of looking at the whole design, which may have, like, for example, maybe 15 or maybe more turbine blades, for example. Now you just focus on these two, and then using some function available in the commercial CFD analyst software, you can basically replicate the same result that you have over here towards other regions. So this is what we are going to, what the figures is trying to describe. Okay? But okay, so the question I have over here, for example, we know that we are just looking at this domain between these two blades. But what happens if you decided to choose a different domain setup? So for example, you decided to use the whole blades, okay, the whole number of blades, for example. And what happens if you choose a different wall boundary condition, which we discussed before? Okay, we have no slip, free slip, roughness, and so on. Okay, so all these choices, all these options available in the software, options are there, but you as a user needs to be able to identify, okay, what is or what are the most relevant options or characteristic or the domain that is suited for your applications. Okay, so if you just want to look at the pressure distribution between these two blades, for example, you might not have to set up the whole domain or the whole domain for the blades. You can just look at the one region between here, and then you replicate the result for the whole domain. Okay, so for example, we're going to come back here. So for example, okay, So this is what happens basically. So just by looking at just this, the domain between these two blades, the results can be replicated to show the result for the whole blade domain, okay, or for the whole device. Okay, so this saves times and also the computational resources. Okay, but you have to understand, you have to make the best judgment whether this method can be used for your particular applications. If we go back over here, all right. So among the boundary condition that can be used in Ansys, okay, if you are just looking at static object, for example, you have just one object that we looked before. Yeah, this is pretty straightforward. I think you can just have the inlet, outlet, and also the wall. You can identify that. But what happens if, for example, this object, instead of a cylinder or a circle, but now you have this cylinder as a moving cylinder, assuming, let's say, you have the vertical axis tidal turbine, okay, for example, looking at from the side view or front view, okay, for example, you have blade over here, okay, or maybe 2 or 3 blades. So what happens when you want to look at the effect or the design rotation at this particular location for the object? Then the boundary will no longer be simple because it involves several advanced boundary conditions that you can use. Okay, for example, when you have a moving blade, for example, if this is your cylinder, you want to have a moving cylinder, you can use what we call as periodic boundaries, okay, where basically now you have, instead of just one boundary for the domain, okay, for the main domain, now you are going to separate. You're going to have 2 separate domains for this is rotational area, and also the outer region, that's your domain, your static domain. So you have to identify, you have to basically put some extra parameters to define these boundaries. So this is what Ansys is capable of. Okay, you might not need to use it now, but just to highlight that the function is available and you can use it for your study. So similarly, for the one that we looked before, for example, if you have the rotating rotor fan, for example, you have the same blade, you can use what we call as this is translatic periodic, okay, meaning that you have shapes that is basically keep on repeating, okay, the repeating shapes. So you can use what is called as translatic periodic boundary. Okay, so all these functions is available in Ansys, and for those who are doing FYP, hopefully you know you have options available to you. All right, so this is about periodic boundary. Basically, instead of drawing the whole device, the whole geometry, you can now simplify your domain to just between 2, oh sorry, this one. You can just simplify your shapes or your domain into 2 simple geometries, okay, between 2 simple geometries, which then the results will be replicated for the whole domain, for the other domain. Okay. Okay. All right. So this is just to check or to show you the difference. What happens if you have or if you use several blades in your domain? Okay. One example to look at or to analyze, how to analyze the domain is quite simple. So for example, if you look at S here, S refers to the separation distance. Okay, so basically, I think the separation distance here is the smallest, 10 centimeter, and then of course we have largest at 60 centimeter. Okay. So if you look at F here, 60 centimeter separation distance. So what you see over here is basically the streamline. Okay, but the problem is we are missing the contour plot. Okay, so we cannot really understand or know what these colors represent. So that's why please keep in mind when you are doing any CFD study, make sure to include the contour plot, okay, the legend over here, so that we can understand what is the phenomena is happening. All right. So just to show you, basically, as I mentioned previously, there are several ways that we can analyze the reliability or the accuracy of our study. We might not have to validate. We have to validate, for example, if you're doing industrial work, you might want to have a detailed validation study. But for example, if you just want to check whether the physics of the simulation is being replicated accordingly, you can use your naked eye, basically, meaning that you use the experience. You know that you have studied fluid dynamics, for example, fluid mechanics, so you know the behavior, what the behavior should looks like. Okay, for example, if you have a larger separation, 60 centimeter over here, for example, okay, you can see that the trailing wave, okay, the separation over here is quite large. And that is to be expected because the pressure is less for this region. But for A, for example, A, you have a separation distance is 10. Okay, so this is 10 centimeter. While you have blades close to one another, so what you will have is basically a higher pressure. So a higher pressure means you have a smaller trailing or a smaller separation at the end. So that's some of the simple analysis that you can do to verify your model. Okay, for example, if you have no idea how to verify, basically you don't have experimental data to verify your output, you can use your knowledge from fluid mechanics. You know what is to be expected, whether the physics is replicated accurately. Okay, so if you look over here, as we go from A to F, okay, as the separation distance increases, you can see that the trailing wave or the separation distance at the back is increasing. Okay, so this basically just one indication to signify that the simulation is producing behavior or characteristic that is to be expected. Okay, that's one simple analysis that you can do. All right, so similarly, aside from the contour plot, okay, usually when you have a contour plot like this, okay, it looks, the behavior is as to be expected. Okay, you have the trailing edge at the end, and then the streamline at the back. Okay, so aside from the contour plot, you can also use a streamline or velocity contour, velocity vector to show the value or the behavior of your flow field. Okay, for example, if you look for the velocity vector on A, okay, this is for 20 centimeter. So let's write it down, 20 centimeter. This is for 40 centimeter. This is for 60 centimeter. Okay. Now, for closer separation, we have a higher pressure, means a higher velocity. So you can see that the velocity, they are quite close up to the surface of the blade. Okay. Similarly, as you have a higher separation, S, you're going to notice that the velocity near the surface is rather lower compared to the free stream. Okay. And as you have a 60 centimeter separation, which is the largest, you can notice that the velocity profile over here. Okay. So the one here closest to the surface of the blade is nearly zero. Okay. And this is to be expected because the pressure and the velocity is the lowest. Okay, because it's the largest separation. Okay, so you can verify your result by naked eye by using your knowledge, using the contour plot, or also the velocity vector. Okay, so if you have something like this and you notice, okay, this makes sense, this is what to be expected, then you can basically proceed to the next step. Okay, so this is just one simple analysis to check whether your result makes sense or not. Okay. Okay. One thing that I want to cover quickly is what we call as the wall function. Okay. Wall function is quite important, especially if you're looking at the region, for example, your area of interest in your study is located near the bottom. Okay. So for example, let's have a look on this velocity profile. So I think this is something that we have looked quite often. Okay, so we have free stream velocity near the surface, okay, for example, and as we go closer and closer to the bottom of our domain, the velocity decreases accordingly. So you can see over here, okay, the velocity vector, the arrow here signifies the value of the magnitude. Okay, so we have a lower velocity vector near the bottom and almost zero near the bottom. Now, so if your area of interest, so for example, you have an object over here, which is very, very close or maybe on the bottom of the domain. Okay. So if you want to create a mesh, okay, in this case, of course, your area of interest is this particular region, okay, near the bottom. Okay. How can you do that? Okay. So previously, when we discussed about mesh, we understand basically, if we have the area of interest, okay, we have to make our mesh more refined in that particular region so that the computation or the simulation can produce a more accurate result, okay, smaller mesh. Okay, but in this particular region, for example, if at the bottom, you cannot produce mesh that is too small. Okay, for example, if the bottom mesh is already, for example, 2 centimeter, okay, then you are going to need a much smaller mesh size, okay, to basically capture what is happening near the bottom. All right. So the law of the wall is a theoretical formulation to add a set of equations that reproduce what occurs between the wall and the wall adjacent to the wall center. Okay? So what it means is the wall function is basically a theoretical formulation. It is an artificial value that is being introduced to your domain, basically to replicate what is happening over here. Okay? So if you look over here, this is the cell and this is the corresponding cell location. You look at the needs for the cell is increasing because we need a more refined cell near the bottom, the area of interest. So we have more cells located near the bottom region. But as I mentioned previously, sometimes we cannot use the size that we want because it is too small to capture what is happening at the bottom. So we need to use one variables or one options that is called wall function. Okay? So the wall function are used to bridge the inner region between the wall and the turbulence fully developed region. Okay? So in this case, the fully developed region is somewhere over here. Okay? So up until here, this is a fully developed region. Okay? But over here, okay, we need a bridge. Okay? We need something that represents what is happening. Remember, when we have a slower velocity, means that we have mixing that is happening violently down here. Okay? And sometimes the software cannot capture these characteristics, okay, what is happening, the mixing. Okay? So if you have area of interest near this location, okay, then if your simulation cannot capture what is happening around this region, then your simulation will be inaccurate. So the wall function, okay, usually they are signified by this symbol y plus. Okay, is an artificial value that is introduced to compensate the needs of the refined mesh over here. Okay, so sometimes by using, for example, if you want to use a resolve, meaning that you want to capture everything in detail, then you need to have, okay, of course, larger mesh size at the top because it is fully developed region. But as you go down, you're going to have a more refined mesh. Okay. But if by using wall function, basically sometimes you can just represent this velocity profile by using one mesh element. Okay, just to show you how the wall function is being imposed. Okay, to basically from here we can get just one element. Okay, so when using the wall function approach, there is no need to resolve the boundary layer, causing a significant reduction of the mesh size and the convolutional domain. Okay, so that's the purpose of the wall function. We do not want to basically spend too much computational resources, okay, because remember, if we have a smaller mesh over here, it represents more work needs to be done to calculate, okay, the variables or the characteristic of the turbulence over here. Okay, so wall function eliminates the need of using a smaller mesh size. Okay, so this is what we looked before. Okay, covered this. Okay. I'm not going to cover this. All right, so I think that's all for the intro to CFD procedures. We have a bit more regarding the Ansys tips or do's and don'ts, which we are going to cover right after this. But basically, we have covered two main parts, which is the philosophy or the intro to CFD, and also the details for the CFD procedures. Okay, we covered in the lab for the hands-on applications and theory in the lecture. Okay, our target is to start with this is basically PDE, partial differential equation or differential equation of the fluid flow, which you are going to start your staff reading on Thursday, and we are going to cover after the midterm break, and hopefully we end with the FDM. Okay, all right. So let's proceed to the next lecture. All right, let's resume. Okay. I'm just going to go briefly. Basically, this is the highlights or the summary of what we have learned, but in terms of specifically for Ansys. Okay, this is Ansys manual basically, which can be downloaded from the internet. I just want to highlight some of the tips, the do's and don'ts when you are doing your CFD case study, right? Okay, so it says here the introduction to CFD methodology. Okay. So what is CFD? I think we covered this before. Just remember the colorful plots that you see is basically based on the conservation of mass, conservation of momentum, energy, and so on and so forth, depending on the modules that you use. Okay. So the relevance of CFD, of course, we look at the different fields where CFD can be used. Okay, we know all this is in terms of conceptual studies, product development, troubleshooting, and redesign. Okay, so we see how CFD basically can save a lot of time and money. All right. The highlights over here, as we discussed in the class, CFD analysis complement testing and experimentation, okay, by reducing the total effort and cost required. So I think this is significant. Hopefully, you can understand by now, CFD is quite powerful, yes, but it cannot replace fully the experimental or analytical solutions. Okay, we still need all of them to basically complement one another. Okay, for Ansys specifically, how does it work? Okay. So for Ansys, the solver itself is based on the finite volume method. Okay. This is FDM. Right. So hopefully, after the midterm break, we are going to cover, sorry, it's not FDM, FVM. To be FVM. Okay. So after the break, we are going to cover FDM, finite difference method first. And then hopefully, if we have time, we are going to cover FVM. So if you students might ask, okay, why do we study finite difference method instead of finite volumes method first, since we are using Ansys? Okay. As I mentioned in the lecture before, we have several methods, discretization method, FDM, FVM, FEM. Okay. All these are relevant in CFD. Okay? It doesn't matter, even though we are using Ansys, which utilizes this FVM method, the finite volume methods. We still need to understand other methods that is available in CFD solution. Okay, so hopefully by understanding one or more of these methods, we can make the best judgment on why one method is more favorable. Okay, not to say one more powerful, but more favorable to one another. Okay, so that's why we start with FDM, and hopefully we can compare the FDM with FVM methods. Okay, so for the Ansys, for the finite volume method, what is happening is that the domain is discretized, or meaning that is being split into smaller elements into a finite set of control volumes. Okay, we have a control volume instead of a finite difference. Okay, and we are going to apply general conservation, okay, the transport equations for mass, momentum, energy, so on and so forth, okay, by using the following set of equations. Basically what we have covered before. We have continuity equation, we have the momentum equation and energy equations. But just to highlight the difference, the main difference between finite volume and also the finite difference is in terms of the calculation method. For FDM, the finite difference method, mostly we are going to use the derivative, dx, dy, dz. For finite volume, mostly we involve integration. Okay, so later on, hopefully we can cover and we can see the difference between these two. Okay, but mainly it's all involved in terms of the mathematical formulations. FDM derivation, the finite volume in terms of integration. Okay, but it doesn't mean FVM doesn't have any partial differential at all. Okay, of course, it's part of the numerical solutions. Okay, right. So we look at this before. Basically, this is the steps that is common. Not to say you must follow this step, but this is the general step for CFD process. We need to define our goal, which is the problem. Okay, we need to identify the domain of the problem. Okay, and then we proceed to pre-processing. So in pre-processing, we need to identify the geometries in 3D model. We need to set our mesh, whether it's global or is it local mesh, localized. We need to set the physics. Is it a second order, first order solver, and so on. Okay, and then we solve our calculations, and then we examine our result. Okay, but this is not a linear process. You need to understand that. So I think you can relate when you are doing a FYP project. In your flowchart, basically, if you have start, okay, your literature review, and then if you set your methodology, more often than not, your methodology will involve some decision. Okay, okay, some decision, and then proceed, and then another decision. Okay, what this means is, if yes, you proceed to the next step. If no, you go back. So similarly, if yes, you go back. If no, you go back. If yes, you go up. So similar to CFD, even though it's not as obvious as the flowchart, decision, and so on and so forth, but most of the time, it involves decision, meaning that you need to validate your result. As I said, you can use your naked eye or your knowledge in CFD to check whether the output that you get, the initial output, does it make sense, for example. Okay, so usually after post-processing, okay, you are going to update your result. Usually you are not just going to run one simulation and then that's it. Usually it is an iterative process, meaning that you keep on repeating the same process over and over again until you get something that you're satisfied. Okay, how to know whether you are satisfied a good result or not? That is, again, you need to verify with analytical model or experimental results. Okay? Or, for example, usually up until here, when you have everything done in pre-processing, and then you try to compute, suddenly you get an error. Then you know something is wrong over here. So you get an error over here. So you know you have to go back either here or here. Maybe your domain is too small. maybe your geometry is not conformal. Okay, we discussed about this. Okay, there are so many potential error. But the good thing about commercial software is that when you try to run the simulation, there will be warning that is given to you. For example, mesh conformal is something is detected. So you know you have to solve something regarding mesh. Maybe you run and then you get some error. So the error will specify, okay, what is the contributing factor of the error. So I think that's why you paid a lot of money for commercial software, because it makes your life easier. Okay? All right. Okay. Next. Okay. So basically, in problem identification, we discussed this briefly. Basically, if you have something, we look at the simple example before. If you have a wind turbine, for example, okay, are you going to draw or to look at the details of the blades or the structure over here? Or can you just make a simple assumption that the blade or the turbine can be analyzed as a circle? Okay? And do you need the structure? Most often, not. Okay? So you need to know what you are trying to solve, what you are trying to analyze. Okay? So you want to check what is the output. You want to check pressure drop, mass flow rate, velocity profile. Okay? So you need to know first what is the main the outcome of your project. Okay? So, and then of course the accuracy that is required. For example, even though you can make assumptions that the blades of the turbine can be assumed to be a circle, okay, you take the diameter of the blade or the diameter of the device. But if you want to look at the velocity profile or maybe the turbulence at the blade, then this method probably is not suitable. Okay? Because by using this method, you just assume the turbine to be one simple circular disc. So you might want to use a more detailed method, which basically utilizes the details of the blade. Okay? So it depends on what you are trying to look at, okay? The accuracy involved. How quickly, say, compared to detail. So let's say if this is our detail design, and this is assumptions or simplification, simplify. Of course, the accuracy for the simplification is less, but it is much faster to compute compared to the detail. Okay? And finally, you need to ask yourself, is CFD an appropriate tool? Okay, usually, once you decide to use CFD, you know the applications can be or suitable to be done in CFD. Okay, usually this is based on your experience. Okay, you know you want to use CFD for what? Then you can basically say in confidence, okay, this is important, we can do it by using CFD. Okay. Then once you identify the problem, then you need to identify the domain. Okay. Now this is a very, very important because I had my IDP group. I think Czech was part of my IDP group last time. So they were trying to look at one system where I think we have something like this. If I'm not mistaken, we have a water tank. This is H2O water tank, and then we need to check the water flow from here to several outlets. Basically, this is watering pot, something like that. Okay. Now, to draw the system, a complete system from the water tank, okay, from the collector, collection point, and then you look at the distribution outlet to analyze everything is quite complicated. It's quite complex. Okay. So what they did basically, instead of looking at this diagram as the domain, they just focus on one simple part. Say use another color. They just focus on the outlet delivery. Okay. So this is what this slide is about. Okay, so for example, if you have a piping system like this, okay, but your interest is only for this part, so you do not need to draw all the other outlets or inlets or the piping system. Just focus for one part over here. Okay? Because, for example, you look at the system, if this is an inlet, okay, and this is another inlet, so you know the inlet over here, you should know the inlet over here, the value, because you need to impose the value. Okay? You should also know the inlet over here because it's connecting, sorry, this is not connected to the system, so it's not a problem. So if you have a large system, so instead of thinking about the whole system, just try to simplify your model if possible to just one particular area that is important for your project. Okay? Of course, it's not to say that you cannot do the whole system. No, but usually if you want to draw the whole system, it is complex. And when it is complex, usually the mesh generation will be very, very tedious, meaning that you have to check the skewness, you have to check whether the mesh conformal is achieved, okay, on so many factors to be considered. So that's why just think about a simple portion, one portion of the overall diagram. Okay. So how will you isolate a piece of the system? Okay, so that's the point. Where will the computational domain begin and end? Okay, so that's the key there. Okay. All right. Okay, so the last one here. Basically, can you use symmetry problem? Okay, for example, if you just have a pipe like we did in the first lab, then you know you can use symmetry boundary condition. So that's you always think about how to simplify your calculations. Remember, not everyone has access to supercomputer or cluster computer. Okay? So you use whatever device or machines that is available around you, laptop, PC, but just remember everything has a limit. Okay, meaning that computational limit. Okay. And then of course, after we identify our domain, we need to have the geometry. So the geometry can be created either in Ansys or outside from Ansys. You can use SolidWorks, you can use CATIA, and so on and so forth. You just need to export the file as .ijs, if I'm not mistaken, to Ansys. From my experience and from my students' experience, usually it's quite tedious to draw your geometry in Ansys. If simple like a square or circular object is quite okay, but if you have several objects, different sizes, for example, you want to create in Ansys, it will be quite tedious. Okay, it's not to say impossible, but tedious. Okay, and for example, if you have something like this, okay, I think this is quite important. Sometimes students just don't get it. You are interested, for example, to check the flow inside the pipe. Okay. The question is, do you need all this detailed shape of the flanges? Okay. More often, no. Okay. Because you are just interested to look at what is happening inside the pipe. So all these, the screws, the nuts, they are not relevant to your study. So it can be simplified to something just like this, a simple cylinder. Okay. So understand what can be simplified. I think that's why take your time, look at your problem, and then look at your geometry. Okay, how can you simplify something into your something that can be exported into Ansys? Okay, all right. And of course, in meshing, we discussed a bit about some of the elements that you can choose. We have triangle, quadrilateral, tetra, hexa, pyramid, prism. Most of the time you can just use the automatic function. Okay, but for advanced user, sometimes you need some customization. Okay, you need to understand for complex shapes, for example, maybe hexa and quadrilateral is not suitable. Remember, because it's structured. Okay, for example, if we have something that involves square and triangle, so to fit everything, maybe you need to choose something that resembles the shapes, okay, tetra or maybe prism or maybe pyramid. So it depends on the problem itself. You cannot just say, oh, hexa is always the best. It's subjective. It depends on the user, what the user wants. Okay. All right. Okay. Right. So what else? Okay. So we discussed before. Basically, we have several options in meshing. We have global. We have localized meshing. That's okay. We also can use a mix of structured and unstructured. Okay. Maybe you can use curvilinear. So be creative. Okay. For complex shapes, you know, you sometimes or most of the time you need to use the unstructured. But if you have a mix of complex and simple shapes, try to mix them if possible. Okay. All right. So okay, this is the issues that we discussed before. Okay. The non-conformal. Okay. So what does it mean? Basically, we discussed this when meshing, where two volumes meet. Okay, the mesh should exactly match. Okay, we discussed before. For example, okay, this is from the left, this is from the right. The face of the element should match. Okay, so you cannot have something like this where, okay, let's say this is face 1 and you have face 2 like this. So this cannot happen. Okay, so the face of the element, they should mix one another. Okay? So if this is a problem, especially when you have several parts combined together. Okay, if you just have one simple part, usually that's not a problem. Okay, but if you have several components mixed together, then you have a problem. Okay, especially when you have multiple parts. So it says here, you have to basically you have to make sure your mesh is conformal before you proceed. Okay? Otherwise, you'll get an error. All right, this is an example of non-conformal mesh, and this is a real example. This is from the work that is being done by my FYP students. So a little bit of overview. So what we have from top view in 2D. So this is our domain, and we have our object here, which is the gray area here. And what this student is trying to do is to have a rotation within the gray area here. So this is rotation area or rotation object. Okay. So at first, when they use the automatic mesh generation, okay, they keep on encountering the error. Okay, but at first, the error was not clear. Okay, what was it about? It says about mesh, but mesh can be so many reasons. But after further observation, you can see that okay, this is, okay, let's say this is domain 1, this is domain 2, this is outer domain, this is the inside domain. You can see that the face of the elements or the mesh from the inside domain does not meet or match the one from the outside or the outer region. And this is what we call as non or not conformal. So let's say non-conformal. Okay? Basically, it means it does not match. Okay? This is a very, very clear example of the mismatch. Okay? You can see over here. Okay? All the mismatch happening over here in the domain. Okay? Okay? Similarly, this is another example from the student. Okay? You can see that here. You can zoom in. You can see that. So that's why it's very, very important. First, you know where to look at. Okay? If you have just one simple domain, no object in it, then there shouldn't be a problem. But when you have several objects, then you need to check the interface of all the objects. Okay, whether their faces meet with the outer domain. Okay, so this is again examples of non-conformal. So where else you can see here? Here, for example. Okay. So this is a real example from my FYP students. Okay, okay, all right. So just imagine this is just for one simple object. What happens, for example, if you have multiple objects with different sizes? So that means you need to check the interface of all the objects. Okay. All right, and then For the physics and the solver, you need to define the properties of the fluid, for example, whether it's just all water or is it interaction between water and air, and so on and so forth. You need to select appropriate physical models. Is it the turbulence model? And then, for example, if you want to look at the heat transfer, you need to activate the energy equation. So operating condition, boundary condition, this is very, very critical. Initial values, solver control, and convergence monitors. Okay. All right. So we discussed about this. This is the rest, what we call it as residual plots. So the purpose of residual plot, hopefully you understand by now, is to check the convergence. Okay? Basically, at the start of the equation, at the start of the calculations, you will see that here, this, if I zoom in this part, what you're going to have a look at is it is fluctuating very, very violently. Okay, if I just zoom in, okay, means that the fluctuation. Okay, why did this happen? First, because it's trying to reach equilibrium. Okay, it's just started, so basically everything is starting at the same time. So you need to understand that. Okay, and then once it started calculating, okay, what does it calculating basically? All these values that you specify, velocity in x, y, z, the turbulence, this is here. Okay, now, so what does it mean basically when you set the convergence value? Okay, so for example, you set the convergence up until 100. Okay, what does it mean? So it means basically you set the iteration, the calculations steps 100 times to check whether they can achieve the final equilibrium. So what does it mean? Because initially, at the start of the calculations, or initially over here, somewhere over here at the start, the calculation does not know the exact value. Okay, for example, if we have a domain over here, and we have an inlet over here and outlet. Remember when I said usually we have V for the inlet and we have pressure. We have P or pressure at the outlet because we do not want to specify the V at the outlet, since we want to check the flow or the outflow happening. Here we want to check the velocity going out. So to do that, the job of the simulation is to find the velocity at the outlet because we did not specify that. So in order to find that, they need to make some guesses. Okay? They need to make some educated guess. So for example, let's say the final value, let's say at one point, we are talking about 1 point, the final value at 1 point is 2 meters per second, just for example. Okay, but of course the simulation does not know this at first. At first, over here, roughly at the start of the simulation, maybe the value that the computer or the simulation started with, maybe, for example, maybe 0.3 meter per second, because the computer does not know the real value. But every time they put some value, they will get, at the end, they will find the value that is correspond to 0.3 meter per second. Okay, what is the output correspond to 0.3? They are getting closer and closer. So as they are getting closer and closer to the, let's say 0.3, and then it gets 0.8, and then maybe 1.2. So it will put some value that is getting closer and closer to the optimal or equilibrium value at the end. So that's why the convergence or the iteration number is important. If you set the value to be too low, let's say 50 iteration, if the equation hasn't been solved or the simulation hasn't reached equilibrium or convergence, then you are going to produce error. Basically, you get an output, you get a contour plot, yes, but your plot is not accurate. Okay, so that's why the numbers here actually is again subjective. It depends on your experience. Usually, just for a simple problem, usually for FYP level, they just use a number between 200 to 400 or maybe 3 to 500 usually. Okay? But as the problems getting more complicated, then you need a higher convergence value, okay? Residual value. So how do you know you have reached equilibrium? You will reach equilibriums when the plots that you have, okay, will no longer fluctuate like this. So instead of like this, it will get steady until the end. So that's how you know that you have reached convergence. So this is convergence, meaning that it has reached the optimal target value. Okay, so convergence is reached when changes in solution variables from one iteration to the next are negligible. So that's why I highlighted over here. Let me add. Okay, so if I make this big, so for example, it started as fluctuating value. Remember, it's trying to reach equilibrium. Okay, this is an exaggeration. Hopefully you understand that. Okay, at one point, the fluctuation becomes smaller and smaller and smaller until you get something like this. Until at the end, the fluctuation is negligible. So you can see that this is almost steady. So this is what is meant by convergence. Okay, so that's why residual plot is quite important. Okay. Okay, so that's why you need to choose. In Ansys, you can choose what are the residual plot that you want to have a look at. So the plot is not there just as a show. It has a purpose. So that's why it's important to understand all the purpose in Ansys. So the quantity of interest which can be selected, pressure, velocity, XYZ axis, can be checked, okay, whether they has reached the steady state value. Okay. So, but more importantly here, the accuracy of the converged solution is dependent upon appropriateness and accuracy of the physical model. Remember, you can have all sort of mechanism to check your calculation, but if your physical model is poorly constructed, the domain is not right, then it's no use. Okay. So you need to go back from the first start, identify your problem, your domain, all the steps. It has to be done properly and correctly. And then secondly, okay, first physical model, secondly is the mesh resolution and independence, meaning that there is one method where they call it the mesh convergence study, which you need to do for your second lab and also for your case study. What is meant here is that you try several mesh value starting from, of course, you try from coarse, medium, or maybe another step, okay, sebelum maybe refine, ultra fine. You can try 4 or 5 mesh setting, localized or global, to check how they influence the output. This is what we call as mesh convergence study. Okay, so for example, I give you some example. If this is one plot and we have another plot, okay, if at one point all the plots behave the same characteristic, or they show the same characteristic, then you know that your mesh difference is acceptable, meaning that whether it's medium, refined, or ultra fine, doesn't have any influence anymore. But usually when you first started, you have no idea how refined should your object be. Okay, so you try with the general setting, and then after that you start with a smaller value. Okay, and then smaller, or maybe and then one value that is larger than the first value to check, because usually, okay, most of the time you will see the difference here. Okay, the difference in characteristic. Okay, right. So this is just an example. So this is for mesh convergence study. Okay, so remember the accuracy of the converged solution depends on 3 things: appropriateness and accuracy of the physical results, mesh resolution and independence, and of course numerical error. Okay, numerical errors, this is depending on what we're going to cover later on the partial differential equations. Okay, basically the values that you set in the physics of the model. All right, so make sure you understand these 2 parts. And of course, for post-processing, I think we discuss this in detail. There are several tools available, but more importantly is you as the user need to make your own judgment whether the output of your result is acceptable or not. Okay. So I think this is understandable. Okay. So at the end, after you have finished with the post-processing, meaning that you have the output, okay, you analyze by, of course, your experience, naked eye, or maybe with data. Okay. Then you need to ask yourself the following questions, okay, which is this one. Most of the time, as I said, you need to update your model. Okay? That's why this is again similar to what mesh convergence is. You finish with, let's say, mesh A, okay, but you will not stop there. Okay, then you will proceed with mesh B, C, D, E, and so on and so forth. That's just one parameter. You can change, aside from mesh, you can also change turbulence model. You can change the inlet, outlet value. You can change the wall boundary. As you can see, there are so many updates or iteration that you can do for your object. So never say, oh, this is my simulation, it's perfect, you can use it for whatever reason. No. Okay? It depends on several factors, okay, based on your judgment. Okay, so the question you can ask yourself, are the physical models appropriate? Okay, check if your assumptions, basically the flow is turbulent, does it exhibit the turbulence characteristic? Is it unsteady? This is based on the inlet value, based on the wall conditions, based on the properties of the domain. If you put something, you know, okay, this should be velocity should be in certain region, the turbulence region, for example. Okay, then does it exhibit the turbulence? If not, you need to go back. Okay. Are the boundary conditions correct? Okay, this is what we discussed last time. How big should your domain be? That's for you to decide. First, let's say you started with this big. Okay, then later on you realize that the flow is not passing through, or the flow basically just stopped over here. Then you need to extend your domain. Okay. The boundary conditions, are they appropriate? And the values, are they reasonable? Okay. Then you check, you ask question, mesh. Okay, can you redefine, refine the mesh? Okay. And remember, this is mesh convergence. Does the result change significantly when refined mesh? So this is what you need to do. Check. Okay. And does the mesh resolution needs to be improved? Okay. All right. So I think we covered this pretty much in the lecture. So this is just the highlight. So again, ask yourself whether the physical model is appropriate, boundary condition, and the mesh condition or the mesh accuracy. So these are some of the examples that you need to ask yourself when doing CFD work. Okay, so I think that's all that I have for today. Okay, all right, so I want to stop recording.